6,000 papers written in the subject, which is really something that it's not common in mathematics. So from 2001 and 2010, many connections were with other areas of mathematics of math were found. And in 2010, cluster algebras entered the mathematical subject classification. I don't know if you know this, but the American Mathematical Society has a subject classification of the areas of mathematics. So every area of mathematics, it's assigned with a code. And then in cluster algebras has a code of, it's an area of mathematics. So it went really, really beyond its original scope, and it became an area of mathematics. In 2010, cluster algebras, is it visible here? Cluster algebras enter the mathematics, the American Mathematical Society mathematics subject classification with the code 13F60. So for example, 13F, this means that it's commutative algebra. And the second number refers about the specificities of the subject. So what I want to actually communicate with this remark is that the field is very broad. So there are many connections with other areas. So maybe you are not interested so much in algebra or geometry or topology, but maybe you are interested in combinatorics or other fields. So there's probability that cluster algebras may play a role in those other fields. Okay, so it's like a very ample subject that nowadays has to do with many other fields beyond these three fields. It's related to analysis. Very recently was related to knot theory. So, okay, so I will leave it here in the history. And if you have any questions about at any point, please feel free to just interrupt me and ask the question, okay? Maybe you are interested in connections with a field that you like. Maybe I know, maybe I don't know, but you are free to ask, okay? So, okay, maybe just to, okay. Maybe just to finish here, I will put like, that some of the main connections. Main connections with other areas of mathematics. We'll put it here. So in geometry, it's better? Okay. So in geometry, the main theories that are related to its tropical geometry. The relation between cluster algebras and tropical geometry is very fundamental. Also with algebraic geometry and symplectic geometry. In particular, a field called mirror symmetry. And this is somehow the area in which I work. Well, it's connection with algebraic geometry and mirror symmetry. So if you have heard about these words and you like them, please come and talk to me if you want. And also with hyperbolic geometry. I also know a little bit about this one, so if you are interested, please let me know. And there are many others, and some others in algebra that I know about are Lie theory and representation theory, and quantum groups. And there's a big etc. here, which I will not talk about. But if some of these lines are familiar to you or are interesting to you, please feel free to ask. Okay. So, okay, that's it about the history of the subject. Now I will go to example first. Okay. So before giving the definition, it's kind of it's not the most natural definition. I will provide some motivation examples. Okay, some motivating examples. So, motivating examples. So, we will consider, first of all, a very... Okay, so... consider the recurrence where n it's a integer where we have the following equation: a n plus 2 times a n. It's a n plus 1 plus 1. Okay? And I consider the initial condition. So as you can see, equation having 3 variables. Okay? So if I specify 2 variables, I know the third. Okay? So I will just give my initial conditions to be a1 to be 1 and a2 to be 1. Okay? So if I fix this recurrence and these initial conditions, I start producing numbers. Okay? So let's see, let's compute them. Okay? So I already have a1, a2. What would be a3? So I use my recurrence. Okay? So I would like to have it's going to be a2 plus 1 over a1, correct? Yes? So this is 1, 1. This is 2. Okay? Now, what would be a4? I do the same, right? a4 would be a3 plus 1 over a2. Okay? And this is 2 plus 1. 2 is 3. Correct? Now, what is a5? a5 would be a4 plus 1 over a3. And this is a4 is 3 plus 1. This is 4. And a3 was 2. This is 4 over 2, which is 2. Correct? Now, what is a6 would be a5 plus 1 over a4, which is 2 plus 1, 3 over 3 is 1. Okay? What is a7? a7 is a6 plus 1 over a5, which is 1. Okay? So I came back to something that looks 1, 1, consecutive 1, 1s. So I know that from now on, here it's just going to be the same. It's going to be 1, 1, 2, 3, 2, 1, 1, 2, 3, 2, 1, 1, etc. And I also know the pattern, right? Just like something that repeats and repeats and repeats and repeats. Okay? So there's like one striking observation that all numbers are positive, which, well, this is not a surprise, because in this equation, if, for example, this and this are positive, then I have, this is the same as an plus 2 is an minus 1 plus 1, a plus 1 over an. So if this and this are positive, of course this is going to be positive, right? So positivity, it's kind of obvious, right? But what is more interesting is that they are all integers. And this is not as obvious. Why? Because we're performing divisions, quotients, right? Here it happened that it was 4 over 2, and that this was and that this quotient is actually an integer, okay? But if I have here 4 over 3, this would not be an integer, okay? So this is less obvious. You think about it, it was not obvious that from here I would only obtain integers. And let's say like the reason to properties, it's that there's a cluster algebra sitting on the background, okay? So the reason there exists a cluster algebra behind. Yeah, so let's say that this is like a very, very, this is going to be an example that will show up very frequently of an algebraic structure that has certain properties that will at least give these two properties just as a consequence out of this structure of a cluster algebra. Okay? So notice, there's another property that is like the periodicity. Right? Which was not obvious neither, right? If you just saw these two conditions, first maybe just think that you're going to get like various numbers. Like another similar kind of recurrence are the Fibonacci numbers. Start with 1, 1, and there's like some sort of relation to get the other one. And then you get like Fibonacci numbers which are just like unbounded and they grow and grow and grow. Here something new happens. I have this periodicity, okay? And let's say that all phenomena will be very obvious once we have an algebraic framework that, like this framework of cluster algebras that governs the properties of this sequence. Okay? Any questions so far? No? So let me first, before like giving the definition of a cluster algebra, explain what's the algebraic structure sitting on behind of all of this. Okay? So okay. So this equation, so explanation, like it's like intuitive explanation, like first explanation of the example. Okay, so the first point is that this equation that I have here, it's an example of something that we call a cluster transformation. First, the equation an plus 2 equals an plus 1 is special. That in my language is going to be is a cluster transformation. has it actually looks like a new variable, and this looks like it's equal to monomial 1 plus monomial 2 over a monomial 3. So these are M1, M2, M3 are monomials on all variables. So cluster algebras are going to work this way. I will have a set of given variables or conditions, things that are varying that I already know, and I will try to produce a new one giving this kind of relations. A monomial plus another monomial over a monomial in between things I know. Okay? So this is like it looks very general, but actually this idea, like the framework of cluster algebras, is making sense of this kind of relations. A new variable, it's a monomial in two variables over the other monomial. And now, as I'm telling you, cluster algebras have relation with other fields of mathematics. So this is a framework that is very general and very that can be modified in many ways. So, for example, we can replace this sum of two monomials by an irreducible polynomial, and there would be a theory of generalized cluster algebras that has been developed, but I will not focus my attention on those. I will focus my attention on this particular class of relations, and I will provide more examples in which this kind of relations actually appear very naturally in geometric examples. Okay, so so this is what we call a mutation. This is what we call a mutation. It is a mutation. And yeah, so intuitively, so maybe just I will put it here. So intuitively, so this is going to be our first approach to the definition of cluster algebras. So it's not going to be completely rigorous. There are going to be some a little bit not well defined, but just to keep an idea of the intuition behind, so that in my following examples, the geometric examples, you can see how what I'm going to write here, it's a little bit more formal. Okay, so intuitively, a cluster algebra A, and I will always work over the complex numbers, is a C algebra so this means a ring, a commutative ring plus a compatible action of the cluster number of the complex numbers on A. Okay, so I have addition, multiplication, a 0 and 1, and I also have a scalar multiplication by C, and you have the compatibility means like the associativity and distributed axioms I will expect hold true. Okay, so possessing endowed, and I will put here, I will underline the terms that are not completely well defined at this moment, because this endowed needs to be made precise. Endowed with a set of generators X in A with the following properties. First, it's that there exists a subset x1 plus xn of this set of generations, okay, such that the rest of the elements X are produced by iterated mutation by mutation of the elements x1 and xn. Okay, so this is the other point which needs to be precise, and I will make these two points precise in my definition of cluster algebra. But let me just show you in this example what do I mean by this statement. Okay, so in particular, I need to tell you what I mean by iterated mutation, and that's like the main technical part of the definition of a cluster algebra. So let me just show you what I mean in this example by this. I already told you what's a mutation. So in this example, let me just erase here. So in this example, I will consider a field F to be, here in my example, there's a number n that comes from somewhere. So in this example, n is going to be 2. N it's going to be 2. And I will consider F to be an ambient field, to be the rational functions on the variables A1 and A2. Okay? So it's just quotients of polynomials in two variables, A1 and A2. Right? So something like this, an element here, it's just G over F, such that G and F are polynomials in A1 and A2, and of course G is different from 0. Okay? These are just abstract rational functions. Okay? I'm not thinking about the zeros of, I'm sorry, F over G. F over G. I'm not thinking about the zeros of G or whatever, so I'm just asking that G is different from 0. Okay? So in this example, my algebra, it's going to be, let's say, it's going to be generated by a set, X, okay? Yeah? And this X is going to have 5 elements. It's going to have A1, A2, okay? And then the others, I already have them sort of here. A3, I already know how to put them in terms of A1 and A2. So it's A2 plus 1, A2 plus 1 over A1, okay? The second one, I want to be A4. But A4 depends on A3. And A3, I already have in terms of A1 and A2. So I just perform the basic computations to obtain that. Okay, I will make it here. So A4, I want it to be A3, which is A2 plus 1 over A1 plus 1. So over A2. So this is just high school algebra, okay? High school algebra, you will have, this is A2 plus A1 plus 1 over A1 over A2. Okay? If you perform this, you get this. Right? Everyone can do that, right? So the next one would be A5. A5, I know that it's A4 plus 1 over A3, but A4, I already have it in terms of A1 and A2. This would be A2 plus A1 plus 1 over A1, A2 plus 1 over A2, right? Over A3, I'm sorry. This is an A3. No. It's an A2. It's an A2, I'm sorry. So A2, it's this, okay? Okay, this doesn't look correct. A1, A2. Okay, I wanted to do A5, so this is A3 actually. Okay, perfect. Now this looks correct. So this looks a little bit more interesting. A3, I already have what it is A2 plus 1 over A1. Everyone is following? Okay. Let me just make it a little bit more clear. Okay. And this looks a little bit more funny. It's not as simple as this. I have to do more stuff, right? So I will just compute it, okay? This is going to be A1, A2 plus A1 plus A2 plus 1 over time A1. So just high school algebra. A1 plus 1 over A1, A2, okay? But this can be simplified, right? This A1 goes with this A1, and this one on top, it's just A1 plus 1 times A2 plus 1, correct? So this goes with this, and this is A1 plus 1 over A2, right? So this is A1 plus 1 over A2, okay? And now I will just highlight something. Here I said that what I obtain are integers, right? And I highlighted here how we are performing quotients that, yeah, in this case were lead to an integer, but this might not have been the case. We can see this actually here. Yeah, we're performing a quotient, right? And somehow this, you remember my initial conditions are A1 over A2. So this is obviously an integer because this is in my initial conditions 1, right? But if this term didn't cancel, this is not clearly an integer, right? Because this guy might be something that is different from 1. But the fact that I have a monomial evaluated in 1, 1, 1, 1, it's always 1. So I would be divided by 1. So somehow, this step here, it's totally related to this observation here, right? At the end, this is obvious that if A2 is 1, this is an integer, right? So this is going to be something that happens general in cluster algebras. Okay? In cluster algebras, I'm going to iterate this kind of computations, but they're going to be way more complicated than this. This is the simplest example, but there's a miracle that will always happen, that there will be a cancellation, and what I will obtain is a Laurent polynomial. So this is a polynomial with coefficients in principle. Let me put this is a Laurent polynomial. So this is, I have variables A1, A2, but I also have its inverses, A1 and A2. So elements are form a polynomial over a monomial. So here, say it's a polynomial in the variables A1 and A2, and this is a monomial this is a monomial. Okay? So this is not any rational function. This is a Laurent polynomial. Okay? A Laurent polynomial is precisely a polynomial divided by a monomial. Okay? And this is going to be something that is going to be a general phenomenon of cluster algebras. Okay? I will start like producing this kind of relations, and at the end of the day, everything will be expressible from an initial condition, and the rest of the elements of the recurrence will be Laurent polynomial in the initial terms. Okay? So, okay, so here I have A5, and then let me just continue. If I write A6 here, this would be A5 plus 1 over A, no, A4, and A5, it's this. It's A1 plus 1 over A2, and A4, it's this one, and this is plus 1. Is A1 plus A2 plus 1 over A1, A2, okay? And if you perform this computation, you will find out that this is just simply A1, correct? And, well, I know that my Blackboard is a mess, so I will apologize by that. If you continue with A7, let me just put it here. Okay, I will erase here. A7 would be A5 plus 1 over A6. A5, I know what it is. A5, it's this, A1 plus 1 over A2 plus 1, and A6, it's, oh no. Did something wrong? Over A1. No, this is incorrect. Let me just write it. I see the periodicity like in these two computations. Okay? The periodicity is a little bit more clear. When I'm expressing everything in terms of the initial conditions, I just continue doing the recurrence of the rest of the numbers, and then these two properties are kind of clear. Why? Because, well, the recurrence is like everything that I'm producing, it's here. Yeah? So the periodicity is clear, and the integers are clear because all of these are Laurent polynomials in A1 and A2. Yeah? So this is 1, this is 1, and this is 1. So that's why I'm having integers, okay? So the cluster algebra in this case would be this one. It could be the subalgebra, this is a subalgebra of my ambient field, generated by these 5 expressions, okay? So here, in this example, my generating set has 5 elements. I have 5 generators. My initial elements are this, and are only 2, and the rest are obtained by iterating this mutation, this formula, and can be expressed in terms of the first in this way, okay? So this is going to be the first example of a cluster algebra, okay? Any questions so far? Yes.
So, can we make our example like why this is particular?
This is going to be, exactly, this is very particular because of this word. When I say iterated mutation, this is going to be a combinatorial framework governed by a graph. There's going to be a graph that it's going to be pre-describing me or telling me the indications to follow this algorithm. So there's going to be an algorithm.
So can we take cluster algebra? These are examples?
Yes, I'm going to give 2 more examples today, and we will see other instances of this Blackboard. And tomorrow I will give a definition in which you will see why this is very, very particular example of something much more general that I will find tomorrow. Okay? Okay, so just by now, I just want to see that this kind of Blackboard makes sense in this example. Okay? Right? So as you can see, let me say iterated mutation. What I mean by iterated mutation, it's all that Blackboard. Okay? All this Blackboard is telling me the iteration mutation. Or if you want, it can be encompassed by this recurrence that allows me to produce the new ones in terms of old ones. Okay? yeah, it's yeah, I know that it's a little bit like general. You don't see like what I'm like the content of the thing, but tomorrow I sure that it's going to make more sense, like because the framework is it's kind of if I just define like the mutation and what I mean, you will not understand why this is interesting. Okay. So any more questions about this example? Yes. It's about the exchange relation? Yes?
A1 equals to 1 fixed these two condition. So if you like change this condition, then still all the conditions will satisfy, like all will remain able integers.
If I change the exchange relations, if they would be integers? That's the question? No, like, no. There might be changes in which there's not a unique new, I mean, here we only see a single kind of condition that we iterate and I produce. So if you can think of this, I have, let me just, let me just erase here and start doing like a graph. So in this case, if you want, you have, from here, I have two things, A1 and A2. And then I have this new way of producing an A3. And here, kind of the equation is A3, it's equal to A2 plus 1 over A1, okay? And then I have a way to produce A4, which is A4, it's A3 plus 1 over A2. So to produce this one, I somehow need A2, and I need A3, and I also need A2 somehow, okay? So I'm just like building a graph, which kind of allows me to think of this procedure, right? Like in every point, I have two things, and like two elements of this field. And I'm labeling the edge, like how I get from, I move from this to this. So this is what we call a cluster, and this is what we call a mutation and exchange relation, okay? So in general, this is a two regular tree. If you see, there are like vertices, and every vertex has two neighbors. But in general, I will have an initial cluster that can be A1 to let's say in this case, A4. Well, it can be an N, but let me say, and I will have 4 neighbors. Okay? And in each part, I will have an exchange relation. Here I will have mutations, mutation, mutation, and here I will have 4 again. We'll have 4 again, have 4 again, we have 4 again, and so on and so forth. So in every vertex, I will have a cluster of things which tell me how to move from that vertex to another vertex. And in each edge, I will be labeling but a similar expression. This is very easy because there's a single expression that allows me to label all these edges. Yeah? In general, it's going to be very complicated. Here, I have many things, and the clusters will be very, very weird, and there will not exist a single equation that tells me how to put everything here. There will be some sort of framework that tells me how to move from one cluster to the other. Okay? So that's going to be more or less the tomorrow definition. I will explain, like, I will start doing these drawings and how I start from a cluster and start mutating to get more expressions, to get an algebra, and this algebra will have several properties that will imply many of these things, okay? Okay. So okay, it's going to be much more complicated than this. Yes?
Professor, as in this example, you mentioned 3 points that all numbers are positive, all numbers are integers, and periodicity.
Yes.
So is this necessary condition that all numbers should be positive?
So
Cluster algebra.
okay, so in a cluster algebra, it's going to be, this is a sequence of integers, and as you can see, this algebra here that I just wrote, this algebra is just generated by A1, A2,
A1 plus 1 over A2, A1 plus A2 plus 1, A1, A2, A2 plus 1, A1, and that's it. So I'm going to provide a framework, the definition that will allows me from a finite set produce a lot. The first theorem, it's going to be that all the things I produced are Laurent polynomials. So like this. So this will imply if I specify the initial guys to 1, I get integers. So you can see the framework is not about integers. The framework is about algebraic expressions. And these algebraic expressions will have properties. In particular, they will have like this Laurent phenomenon. And the Laurent phenomenon implies that if I specify the first ones to 1, I get integers. So that's how I get back to integer sequences. And in general, they don't need to be sequences. They can be collections of integers indexed by vertices of a graph.
So, Professor, when I get that, these are just complete of specific examples.
Yeah, this is like the simplest non-trivial example. Okay, simplest non-trivial example. Okay, and in general, I mentioned about like lots of other fields of mathematics. There's a particular case where I have like my the collections of integers are of 3 numbers, A1, A2, A3, and then I have to mutate in 3 directions. These are connected to the Markov numbers that appear like in other areas of mathematics, in number theory, in hyperbolic geometry. So there are also like, in this kind of explanation, you can see connections to other areas of mathematics, okay? Okay. So let me just give another example, which is geometric. Okay, it's a geometric example, and it's not about a sequence of integers, it's about a variety and the functions on that variety. Okay? Any more questions? Yeah, okay. So I will not erase this one. So I will close this example, okay? For the next example, it would be convenient that I know a little bit about algebraic geometry. So raise your hand who knows a little bit about algebraic geometry. Okay, 2 persons. Okay, so I will give a very short introduction of what I mean by algebraic geometry. So okay, so let's put a definition. And I will put in parentheses affine an algebraic variety V is the solution of a system of polynomials. Okay? So more precisely, if I have f1 to fs are polynomials in, say, n variables, x1 to xn, okay? Okay, I have the same x. It's not an accident that this x and this x are the same. At the end of the day, they are going to be identified. But no worries for the moment. So here V, I'm going to use the notation, it's going to be the vanishing set of F1 and Fs. This means that these are all the points, all the vectors A1 to An in C to the n, such that Fi evaluated in A1 to As to An, it's equal to 0 for all j. Okay? So I have S polynomials and I'm just asking for the solution set of that set of polynomials. Okay? This is a subset of C to the n. Okay? And I put the word affine because there are other varieties that are called the projective varieties, okay, that are going to be important. I will go back in a second. So the other definition is the ring. I will use the ring of functions or the ring of algebraic functions of the coordinate ring. The coordinate ring of this V, which is the vanishing set of some set of polynomials. The coordinate ring is, and I'm going to denote it like this, like polynomials in V is, I take my ring, and I just divide it, I quotient it by the ideal generated by the polynomials. Everyone remembers what's an ideal and what's the quotient construction for rings? That's basic algebra, okay? So this is the ideal generator. By F1 to Fs, right? And this is just a quotient ring, okay? So if you think about this, the notation suggests that these are polynomial functions on V, right? Because these are the polynomial, so what I have here, I have C star, right? Cn, and somewhere here I have my algebraic variety. This is V, right? So all elements here are all the polynomials that can be evaluated in the ambient space. But some of those polynomials will not give a well-defined function on V. Yeah? But precisely any element here in this quotient will give a well-defined function here. Just think about it. Maybe this is the first exercise. Like the first exercise is like, see that this can be identified with the polynomial functions on V. This is like the set of polynomial functions on V. Okay? Okay, so that's a very important thing. And then I will say that V is projective if F1 through Fs are homogeneous polynomials on the variables. Right, so okay, so for example, this is not homogeneous. A1 square, x1 square plus x2 square minus 1, yeah? If I only have a single polynomial, this would be the equation of a circle of radius 1, right? So this is the variety, it's just a circle of radius 1, right? This is not homogeneous, it's not a projective variety. But if I have x1 square plus x2 square minus x1 x2, this is homogeneous. And this is not homogeneous. Okay? So homogeneous is that it's a sum of monomials and all the terms have the same degree. I have degree 2, degree 2, degree 0. It's not homogeneous. Degree 2, degree 2, degree 2, it's homogeneous. It gives rise to a projective variety. Okay? So in this case, if B is projective, in this case, if B is projective, then V, it's going to be a subset of the complex projective plane of dimension n-1, and this is just C, it's Cn minus S minus 0 plus mod a relation, and I say the two vectors are related. V, a vector, is related to another vector W if V, it's an integer, it's a multiple of W for some non-zero complex number. Okay? Yeah. So maybe second exercise. This is I'm not going to put them as exercise right now. I'm going to put them. I would put the actual exercise in a second, but it's just like that. It's just like an intuitive exercise. Like convince yourself that this set can be thought of in your head as polynomial functions on V. Yeah? Like the functions on V that are polynomial. Okay? And the second exercise is to convince yourself that if V is a projective variety, so if V is a solution of a system of homogeneous equations, then V can be thought of as a subset of the complex projective space. Okay? Okay, so I will give an example of a projective variety that will have a cluster structure. Okay? And I'm saying a keyword right now, cluster structure. So this framework refers to structures. These are not properties. It's something. These are two different things: a property and a structure. A property, it's like something that holds for some space or for some algebra. It could be. An algebra could be an integral domain. That's a property. It could be reduced. It could be finitely generated. Those are properties. Structures are something that you put on top. It's like putting a dress. You can change of dress. It's not a property, okay? So I'm going to give an example of a projective variety, and I will show you what's the cluster structure, so how this framework fits into this example, okay? So let me just put an example. And the example is going to be interesting. So the first example is, I'm not going to start with the polynomials. I'm going to describe the variety, and then I will try to argue that this is an algebraic variety, okay? A projective variety. So V is going to be a Grassmannian. I don't know if you know it. If you know this space is the Grassmannian of two-dimensional place in C4. So as a set, this is just the set of vector spaces. W is a vector space of C4 such that the dimension of W is equal to 2. This is the dimension of V thought as a complex vector space. Okay? This is an element of linear algebra. I don't know if you have seen it before, the Grassmannian. Yeah. Raise your hand if you already have seen the Grassmannians before, or this is the first time you saw a Grassmannian. Who knows Grassmannians? No one? Okay, interesting. So this equation, here I can put a K, and I can put an N, and it's just going to be the set of subspaces of Cn of dimension K. Okay, so this is an element of linear algebra, and for example, the Grassmannian 1Cn, it's just identified with the projective space of dimension n-1. Yeah, the projective space can be thought of all those complex lines. Yeah, so a complex line is just like a one-dimensional vector space that passes through the origin and mod this relation. And if you think about it, this is the first exercise. This is exercise 1. Exercise 1. prove this equality. Yeah, that the complex projective space can be identified with the Grassmannian of one planes in Cn. Okay? So these spaces are somehow the generalization of, so let me just put like here, well, like put it correctly. Okay. Okay. So, so Grassmannians can be thought of as generalizations of complex projective spaces. And from this definition, it's not clear that it's an actual algebraic variety, right? Here I'm just putting you the set of subspaces of a given dimension, right? It's not clear that that's actually a variety. But it's actually some of the most important, well, there are distinguished examples of projective varieties. So there would be, for every k and every n, there would be homogeneous polynomials, such that this set can be identified with the variety determined by that set of polynomials, okay? So let me just give the first example. Example, k equals 2, n equals 4. So this is going to be a projective variety defined by a single equation. In this case, this Grassmannian is going to be defined by only one equation. So it's going to be the zero set of a polynomial, or of a homogeneous polynomial of degree 2. And okay, it's as follows. So first of all, I'm going to so first of all, I'm going to define a function from the Grassmannian 2, 4 to CP4. Okay? Aha. Okay, so CP4, it's just a quotient of C5, is C5 minus the origin modulo this equivalence relation. Okay? And I'm going to build these functions as follows. So here I have a vector space. Okay? So I need to say to what I'm sending it. So first I will give notations for the coordinates of here. So if I have a projection from C5 minus 0 to CP4. So here if I have an element A1 to A5, and I will, usually one puts A0 to A4. I go to, I call it, its class. This is just the projection. This is a quotient, this is an equivalence relation. So given an element here, I can see what's the equivalence class it's mapped to, and I will call that class A0 to A4. Okay? I will just change, instead of putting like, you know, like a class like they put here, I will just put brackets and put 2 dots here everywhere. Okay? So here I will have to send it to something. Well, it will have like 5 entries. It would be, well, it has to have 5 entries. 1, 2, 3, 4, and 5. Okay? It needs to have 5 entries. Okay? But I'm going to do a trick. Instead of using the original notation, I will use a convenient notation. I will use convenient notation. So instead of taking like these coordinates A0 to A1, I will take coordinates coordinates of CP4 will be written as follows. So I will have a coordinate A12, a coordinate A13, I will have a coordinate A14, a coordinate A23, and a coordinate A24, okay? So these are 5 numbers, okay? So instead of using 0, 1, 2, 3, 4, I will use it 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. How to remember this? I just have a quadrilateral with 1, 2, 3, 4, and these are the and I need also, I'm sorry. I'm missing something. Actually, this goes to CP5. So this is from C6. So everything increases by 1. I need 6 coordinates. Okay? I need 6 coordinates, so I'm still missing a coordinate here that it's A34. Okay? Yeah? So how to remember these coordinates are the 6 different diagonals and edges that I can put in a quadrilateral with 4 vertices. Okay? So this and this is just the following. It's just the same, but this is going to be more convenient. Why? Okay? W, it's a 2-dimensional space in C4. So a 2-dimensional space is generated by 2 elements. Okay? So I will just choose. So choose W1 equals to W11, W12, W13, W14, and W2, which is W21, W22, W23, W24, generators of this set, of this space, such that W is just the generator of W1 and W2, okay? Just pick a basis, any basis you want. Just choose. So there's a choice, okay? You choose a basis, and then what you're going to map set W, it's center ij, right? With this 1 less or equal to I less than j less or equal to 4, okay? So the set of these different entries, it's going to be the determinant of the matrix W1I, W1J, W2I, W2J, okay? Now this labeling starts to make sense. Why? I'm in a 4-dimensional space, and any 2-dimensional space has a basis with 2 vectors, okay? This collection of pairs of, this collection of lines or diagonal in this quadrilateral are just choosing me a submatrix of 2 by 2, a 2 by 2 submatrix of this 2 by 4 matrix that I can form with these 2 vectors. Okay? And if I have a square matrix, I have a determinant. Right? So I have dimension 2, that's why I have 2 entries, and the positive, these are choosing me the possible columns that I can choose in this 2 by 4 matrix that lead to a 2 by 2 matrix so that I can compute the determinant. Okay? So, for example, this would be I'm sorry, I put it here. This is the determinant of the matrix W1 I, W1J, W2I, W2J. Okay? So this is my map. This is my map. This is just W12, W13, delta W 3, 4. Okay? Example. If my hyperplane is just generated by the vectors 0, the canonical basis. Okay? Then delta of W, it's going to be, so I have to make this matrix 1, 0, 0, 0, 0, 1, 0, 0, and then start choosing this rectangular, if it's square submatrices. So first two, this is the identity matrix has determinant 1. Okay? Then I choose this column and this column. I get this matrix. Okay? Determinant is 0. Then I get, if I choose first column and third column, I get the same matrix, determinant 0. So on and so forth. Okay. Okay? So first exercise. Exercise number 1. Well, this is exercise number 1. Exercise number 2. The map is well defined. Okay? Why is well defined? What's the exercise? I have to show that this map is independent of the choice of basis. Yeah. For example, if I choose another guy here, for example, the 7, 0, 0, 0, and then the 0, minus 4, 0, 0. These two vectors correspond to generate the same space. If I take the map using this basis, what I get it's I get something very similar, but I will just have the determinant of this matrix, right? Which is 7 times 4, which is 28. 28, 0, 0, 0, 0, 0. These are the same thing in the projective space because these are multiples of each other. Okay? So the exercise is to show that, well, I can choose primes here, and then what I get it's vectors that are multiple of each other. Okay? Exercise number 3. Show that for every W point of the Grassmannian 2C4, I have that delta 1, 3 of W times delta 2, 4 of W. It's equal to delta 1, 2 of W, delta 1, 4 of W, 3, 4, plus delta W. This is sometimes it will happen all the time. Here I put like the coordinate ij, and sometimes I put it here, like the determinant ij. So these two are the same, okay? I'm sorry. So this is 1, 4, 2, 3, W. Okay? How did I remember this equation? I just wrote it like this. How did I remember? It's again the quadrilateral. 1, 2, 3, 4. Okay? You might remember a Ptolemy theorem that says when I have a quadrilateral sitting inside a circle, then the product of the diagonals it's equal to the sum of the product of opposite sides of the quadrilateral, and this is exactly what it looks like. These are diagonals, 1, 3, 2, 4 diagonals, and these are opposite sides. 1, 2, 3, 4, and this is the other opposite side. 1, 4, 2, 3. Okay? So this is what people say like a Ptolemy relation. And they also have the name Plücker relation. I will comment on this later, but okay. So this is a very easy exercise, right? Delta 1, 3, this would be, like you choose a basis, and it's just like this is just like a polynomial example. For example, this one would be W1, 3 times W2, 3 minus W1, 2, 3, W, 3, 2, 3, 1, 1, I'm sorry, 1, 1, 2, 1, W, 1, 3, okay? So all of these are terms that look like this, and you just have to check that the relation is satisfied. Okay, this is an easy exercise. Okay, so what do you notice about this equation? It's a polynomial equation in 6 variables, okay? So I have 6 coordinates, and I have 6 variables, okay? And it's homogeneous. This is degree 2, this is degree 2, and this is degree 2, okay? So this exercise implies that delta GR2C4 is contained in the vanishing of the polynomial x13, x24 minus x12, x34 minus x14, x23. Okay? Yeah? This is just contained, this is like this polynomial. It's a polynomial in 6 variables, in variables x, I, j, such that 1 is less or equal to 1, to I, j, and 4. Okay? Right? So I have polynomial with 6 variables that is homogeneous. So this means this is a projective variety, and the last exercise 4, is that this is not a containment, it's an equality. Yeah? Is that delta Grassmann 2C4, it's equal to the vanishing of that polynomial. Okay? Not just contained. Okay? This shows that this is a projective variety. Yeah? And also maybe want to show this, and that this is injective. And this exercise will imply that Grassmann 2C4 is a projective variety. Okay? Okay, I'm running out of time. Can I take 5 minutes just to explain how? Yes? Okay. So the point was to have a ring and show that this ring comes from an algebraic variety, and that this ring kind of looks like this framework. Okay? I'm almost there. Okay? I'm about to have it. So what's the purpose of all these 2 things? It's just to show that the Grassmannian 2,4 it's a projective variety. Okay? So here I'm embedding this set to the projective space, and then I'm saying that the image of this delta it's injective, and its image it's a projective variety defined by a single polynomial. Okay? So that's the purpose of this exercise, just to show that this Grassmannian it's indeed a projective variety. Okay? Defined by a single equation. That's what we call a hypersurface. It's a hypersurface in C6, in C5. Oh. I'm sorry. Here I put the numbers well, but I then change here. This is 6, and this is 5. Okay. So this is a hypersurface here. So this is 5-dimensional. It's a 4-dimensional variety. Okay. It's a 4-dimensional variety, 4-dimensional projective variety. Now, claim. So from what now on? So we identify Grassmann 2C4 with its image, which is image of delta, which we know it's just the vanishing set of x13, x24, minus x12, x34, minus x14, x23. Okay? So now I'm thinking of this Grassmannian as a projective variety. Okay? So claim, and this is like in quote marks, Grassmann, the coordinate ring of functions on this Grassmannian is a cluster algebra. Okay. So I have to show that something similar to the first example holds for this example. Okay? And it's going to be actually simpler than the first example. It's going to be much more simpler. It looks way more complicated because the narrative is a little bit more complicated. I have like this variety on the space, but now you can forget about the variety and just think of the following ring. What's this? This is just going to be the polynomial ring in variables xij, such that 1 is less or equal to I, it's less than j, less or equal to 4, mod this polynomial, x13, x24, minus blah, blah, blah. Okay? So here I have to construct a set of generators and a way to produce the rest of the generators as follows. Okay? So what I claim is that, well, this is generated, obviously, this is generated by the class of x13, the class of x12, x13, x14, x23, x24, and x34. Okay? Because they generate the ring. Before I do the quotient, the variables already generate the ring. So their images will generate the quotient. Okay? So I will put this is my set X. Right? And here n it's going to be equal to 5. N it's going to be equal to 5. Okay? So I have 6. 1, 2, 3, 4, 5, 6. So I just need to produce the other one by a mutation or something that looks like a mutation. Okay? So I know that these guys satisfy this equation. Right? I know that, so here I will put my first initial set to be x12, and I will just change a little bit the order, and you will see why. x13, and then I have x12, x23, x34, and x14. Okay? So if you think of the quadrilateral, 1, 2, 3, 4, my initial cluster, my initial set of variables, this is the initial cluster, it's all the sides of the quadrilateral plus one diagonal. Okay? And I'm missing another generator that is 2, 4. It's the other side of the diagonal. So what I'm missing is the one corresponding to this one. So I know that this satisfies this relation, and this is going to be x24. It's equal to x12, x34 plus x14, x23 over x13. Okay? This looks a lot like the relation in the first example, a sum of two monomials divided by a monomial, right? So this looks like a mutation, okay? And that's it. I have a generating set. I have a subset of the generating set, and the rest of the elements can be obtained by iterated mutation from this set. So, okay, so this is the generating set has 6 elements. The initial cluster has 4 elements, and the remaining one it's given by this thing that looks like a mutation because it's a monomial plus a monomial over a monomial. Okay? So it's kind of easier than the other example. Do you remember that in the other example I made like this graph in which I'm telling you like I have a, I have a certain cluster in each vertex, and I have like an exchange relation in each one. This is a 2 regular graph. This is a 2 regular tree. I will call it T2. This is the only connected graph which is 2 regular. Every vertex has 2 neighbors, right? Here I have a 1 regular graph. This guy, this one, this is T1. This is a 1 regular graph. Here I will have the cluster produced by, and instead of writing all these things, I will just put my quadrilateral, and I have this guy. And in the other, I have the other one, right? Here I have 5 generators indexed by all these sides and diagonals of the quadrilateral, and here the same. So I will put this in other color. If I had blue, I would put it in blue, because these are in all clusters. These are the frozen ones. They don't change. But I mutate a single variable. Okay? So this is the cluster structure. This blackboard is the cluster structure, like telling you which are the generators and how they can be produced by a subset by iterated mutation. That's the cluster structure, and somehow all that information is in this blackboard. Okay, so that would be like the cluster structure of the ring of coordinates of the Grassmannian of 2 planes in a 4-dimensional complex vector space. Okay, so I will end up here. Just let you know, I just want to let you know that for every k and every n, there will be a cluster structure. It's way more complicated as I vary the k and n. So Grassmann 2n can always be put in terms of a quadrilateral, of a polygon. So here, k is 2, and I have a 2 plus 2, a quadrilateral, a 2 plus 2 gon. So if I would have here 2, 5, I'm sorry, I have an n here. This is an n-gon, okay? So if I will have like 5, I will have a pentagon, and I will talk about triangulations of a pentagon. So the drawing looks a little bit different. So for Grassmann 2,5, the cluster structure would be encoded in the triangulations of a pentagon. And there are like, the mutations look like flip of quadrilaterals. If you look at this diagonal, I just flip it. So here, this would be like kind of related to the cluster structure of Grassmann 2,5. I hope I did it correctly. So there are going to be 5 clusters, and this is going to be related to the first example, the recurrence that had also 5 terms. And if I have more things, like for example, Grassmannian if I have Grassmannian 3, 6, what I will have is triangulations of an hexagon, right? And these are encoded in something very beautiful that is called the associahedron. I don't have the picture, but it's like a 3-dimensional thing. That looks somehow like this. So every vertex will be like a triangulation. This would be, for example, this triangulation, and of a pentagon, of an hexagon. And I start flipping around the things. I can flip 3 things, so that they have a 3-regular graph. And well, they are organizing this polytope, which is the 3-dimensional associahedron. So that's like a connection to algebraic topology, where this associahedron also show up. Okay, I will end up here.